food, drugs, or ideas, what you consume influences who you become. On the Mind and Matter podcast, we learn together from the best scientists and thinkers alive today about how your mind-body reacts to what you feed it. Before starting Mind and Matter, I spent 10 years in academia doing scientific research. I got a PhD in neuroscience where I focused on neuroendocrinology and the neurobiology of behavior, and before that, I specialized in molecular, developmental, and evolutionary genetics. I use my scientific background to help parse and translate the information that guests share on the podcast. In addition to the podcast, I write long-form written content inspired by the show where I integrate what I've learned across episodes. I also have a free weekly newsletter where I provide you with upcoming guests, share links, and provide commentary on scientific studies and research that I'm reading, and more. Visit mindandmatter.substack.com to find all of my content. You are about to listen to the full episode, but there will be 1 to 2 short ads immediately following this before the conversation. If you would like to hear ad-free episodes and get early access before they release more widely, become a paid subscriber at the Mind and Matter Substack at mindandmatter.substack.com. Becoming a paid subscriber is a way to directly support my efforts, allowing me to make more episodes and higher quality episodes, and also helping to free up my time so that I can spend more of it on doing research and synthesizing results from the podcast and from the literature so that I can do more things like writing on the Substack, putting more content into the newsletter, and getting these things out more frequently. So if you want to support the show and get ad-free episodes, go to mindandmatter.substack.com. Hey everyone, I want to take just a minute to tell you about a really cool health monitoring device I've been using called Lumen. It's a handheld, pocket-sized device with a sleek design. The Lumen device measures CO2 levels in your breath, which allows their technology to determine the extent to which your body is burning fats versus carbohydrates. Lumen helps improve your metabolic flexibility, your body's efficiency in shifting between using fats and carbs for energy. I use this device in the morning or before bed or after meals or after workouts to track my metabolism. With just a couple weeks of use, I learned a lot about which foods were causing my body to burn mostly fat, mostly carbs, or both, as well as how long I needed to fast and how hard I needed to exercise to promote fat burning. Being able to track whether your body is burning fat versus carbs will help you figure out how your body responds to your lifestyle and whether or not your weight loss and fitness strategies are actually working. Lumen is great for anyone looking to optimize their health for either weight loss or athletic performance. Their easy-to-use app allows you to track your results together with what you're eating and how you're exercising, and it syncs with other devices like the Apple Watch. Click the link in the episode description to learn more and use the code MINDMATTER, MINDMATTER, to get 10% off your Lumen device today. That's on top of the site-wide sale they are currently running, and the Lumen device is eligible to be paid for with FSA and HSA health accounts. Check out the link in the episode description for more info.
It gives the background of where we both come from, and it's also it's been an adventure in interdisciplinarity for me. I was when I finished my astronomical career, I decided not to actively continue with that, although I do to some extent. But I realized I wanted to broaden out and become more multidisciplinary.
Mm-hmm. So your background, your formal background, your training is in physics.
It's in that, well, yes. I mean, it's in physics. I got a physics degree, but it was then in astrophysics. I did my DPhil in astrophysics, and that was at the Royal Greenwich Observatory in Sussex. Really, when Britain was making the transition between classical positional astronomy and astrophysics, so we were right in at the beginning of the astrophysics research in observational research in astronomy in Britain. And so I've been through the whole process from there to James Webb Space Telescope, and it's been an amazing adventure.
Yeah. And so how did you get your start working with someone like Glenn Jeffrey?
I saw I was on an interdisciplinary fellowship in Durham University. It was set up to bring, I think, a dozen fellows together from totally different fields: poets, historians, scientists, whatever, and bring them together and locate them in one place in Durham. Very beautiful place on Palace Green next to the cathedral. And we could sort of roam the university and give talks about our own subjects and mix with all the faculties and so on. So this was an introduction to genuine university-based interdisciplinarity. And I just one day I saw a video released by the BBRC, which is the biological research agency in Britain, on reindeer vision in the Arctic. And I'm interested in light and natural light and color and things like that. So I watched this video, and at the end, he showed a couple of ultraviolet pictures that I'd taken. They weren't related to the subject at all, but I thought, well, that's a bit much. You didn't ask my permission. So I sent him an email and I said, I was very interested in your reindeer paper. I said, there was one thing you missed out in the paper, and that's why the reindeer have to cope with very blue light in the Arctic winter. And I mean, I knew that, but obviously he didn't know that. So I said, I was surprised that you didn't mention this. And he wrote back the next day. So I'm quoting him verbatim, excuse the language, but he said, "Oh shit, I knew we should have had an atmospheric physicist on the team." So we kind of got on quite well together, and we had lots of telephone conversations and so on. And I eventually started visiting him in his lab in University College in London. It's in the Institute of Ophthalmology, which is next door to Moorfields Eye Hospital.
Yeah, yeah. But why was he studying the reindeer?
Well, he was interested in vision in its broadest sense. So he studied animals. He had various animal models. And he'd spent quite a lot of time in Tromsø working with the Sami people on reindeer. So he was able to collect reindeer eyes from their normal husbandry of the reindeer. And they didn't kill any reindeer specifically, but he got a lot of eyes. And they'd already written a paper on why the reindeer eye is so different.
And what's different about it? I can imagine why they live in this northern latitude, and so the sunlight environment is going to be very different than it is.
Well, it's actually the only difference is the long twilights, and twilight is extraordinarily blue because of ozone absorption in the atmosphere. I mean, this is a very well understood atmospheric phenomenon, but it wasn't widely understood or known by biologists or medics or anyone. And I'd studied this, and I told him this, and it gave us a background in order to understand the phenomenon. The phenomenon is extraordinary because the reindeer, it's a bovine. It has a tapetum lucidum, a reflector behind the retina, made of collagen fibers, and it changed the color of the tapetum between summer and winter. In the summer, it was a sort of golden color, like cows and deer have normally. But in the winter, it turned this deep blue, absolutely beautiful, deep, very deep, pure blue color. And it was clearly a photonic process. Anyway, I started working with him, and we picked apart the mechanism by which the reindeer actually changed the color during the winter. It adjusts the spaces between the collagen fibers and makes a Bragg reflector with a shorter wavelength. And anyway,
So the spacing between collagen fibers dictates the color of this structure.
yes, because it's a two-dimensional Bragg reflector. And that's the only way you can generate color, because you have nothing in there that reflects very strongly in the eye. It's just collagen and water and stuff. And so to make a high quality reflector, you have to build an interference structure. And the interference structure in the summer is tuned to redder light, and in the winter it's tuned to blue light. And it's a little bit of a sideline, but in fact it's very relevant to what I'm talking about today, because having structural colors in animals is very common. We all know brilliant bird feathers, butterfly wings, and all of these things, chameleons, and all of these structural colors in animals, but nobody's ever really thought of structural colors in normal mammals, like us. We don't obviously have structural colors. But in fact, we're realizing that we do have a number of highly ordered nanostructural items in our bodies. And this plays an enormously important role in the harvesting and transport of light in our bodies. And so there is actually a close connection. And I can come to that later. That's a very important part of the story. But
Yeah, yeah,
we're full of nanostructures which interact with light.
yeah, yeah,
And so that was an interesting introduction to that particular topic.
yeah. And so I think we'll definitely circle back to that when we talk about the interaction
Mm,
of humans and other animals
yeah,
with light on
yes.
Earth. But, given your background, given that I'm talking to Bob Fosbury here, the astrophysicist, I want to start with the sun itself because this is an area where, I'm definitely going to be way outside the realm of my expertise. And I don't know that much about the sun from an
No.
astrophysics perspective. Can you just start off by giving us kind of the basics of the sun? Like, what kind of star is it, and what are its major characteristics as a star?
Yes, well, I'm happy to start with that. I wasn't going to start with that, but I'm very happy to start with that. I mean, stars are the first stars formed about 2 or 300 million years after the Big Bang. There was a long period of darkness in the universe between the emission of the cosmic microwave background and the first stars, and it was called the Dark Ages, in fact. And now with Hubble and the James Webb and some ground-based telescopes, we're trying to find the first stars, the very first stars that formed. And the James Webb is getting very close to doing that. And actually, I'm involved with that. I'm actually publishing papers on that now. And it's a very exciting topic because, of course, the first stars uh, didn't yet have access to the whole periodic table because
Mm.
there was only hydrogen and helium formed in the Big Bang. And so, my introduction to this talk with stars is to say that they are the origin of the periodic table. And it's the stellar evolution from this first few 100 million years to now, which has populated the universe with elements heavier than hydrogen and helium and lithium. And this actually links very, very closely to what I'm going to say about life. Because if you consider a star is, in simple physics, a star is collapsed gas. You have an interstellar medium which is full of hydrogen and helium. We're talking about the first stars now. And it's slightly inhomogeneous because the initial quantum fluctuations in the Big Bang imprinted on the structure slight variations.
So it's close to homogeneous, but not quite.
Yeah, exactly. And so when the cosmic microwave background that was emitted about 380 million years after the Big Bang, sorry, 380,000 years after the Big Bang, carried those slight fluctuations in its structure. And if you remember these maps of the microwave background, which you've seen from Kobe and WMAP and Planck, they're usually colored a mixture of blue and red with sort of grainy fluctuations all over them. That's the imprint of the inhomogeneities in the early universe that comes from the original quantum fluctuations. And those fluctuations enable gravity acting on gas in the early universe to begin to clump because
Mm.
the slightly denser regions
So there,
would
yeah, there
clump
just happen to be
preferentially.
some regions that are slightly denser, and
Yes,
then that causes a gravitational
exactly.
pull there. Okay.
Yeah, so they clump and eventually they form stars, and it's quite difficult to form the first stars for an astrophysical reason, and that is when you form a star like the sun, the gravity collapses it, and like a bicycle pump, it heats up the interior as it collapses and collapses,
Mhm.
and eventually you reach temperatures that enable nuclear fusion in the core. And in order to reach that, you have to cool the surroundings because the surroundings are getting very hot,
Mhm.
and the heat discourages the compression. And so a normal star like the sun can radiate its heat through the metals,
I
through
see.
the
So,
heavy elements.
so at the core of this, there you need very, very high heat to get nuclear fusion,
Yeah, yeah,
but heat expands, and so
Yeah.
in
So
order to
you
keep this
establish,
compression happening, you need to cool the outer part.
yeah. And so what happens is the star gradually collapses until you reach nuclear fusion in the core, burning hydrogen to helium. And that's about, tens of millions of degrees, depending on the mass of the star and so on. But the, uh, the the outer region has to cope with all the heat that's been generated by the collapse. And so the star, once it reaches this equilibrium between the force of gravity and the pressure due to the very high temperature in the core, it reaches a state of not thermodynamic equilibrium, but it reaches a state of sort of kinetic thermal equilibrium in its internal structure. That's a lower entropy state than the original random nebula.
I see. So that is now
So
stabilized.
in order to reach that semi-state, that metastable state, it's had to export entropy.
Hmm.
And the entropy is exported as starlight from the surface. That's the way a star gets rid of its entropy. And so that you set up a structure which is metastable over millions of billions of years. I mean, it's stable over billions of years until you eventually run out of fuel. It's stable for billions of years, but it's it's structured so it's relatively low entropy in its structure, but it's generating entropy as it has to radiate heat
So
out to the surface.
in order to maintain that stable state, the star has to give off what we can think of as a waste product, and it's light.
Yes, and the waste product is light, and the light is actually waste entropy. But the photons are very low entropy, of course, and that comes back when we talk about life.
Hmm.
So a star is basically it's a state of temporary hydrodynamic equilibrium between a very hot core and the overlying gas, which is gravitationally attracted towards the core. And that maintains the state where you can continue nuclear fusion processes actually very, very slowly. It's like a very, very, very slow hydrogen bomb. I mean, if you're a proton, you have to wait a very long time before you get fused into helium. So it's a very slow, gentle generation of heat. Obviously, gamma ray photons come out. They're very low entropy, but when they've scattered all the way up to the surface, which takes hundreds of thousands of years to get to the surface of a star, get the heat from the center
Hmm.
to the surface. If you switched off the nuclear fusion in the center of the sun, you wouldn't notice for hundreds of thousands of years. It
Wow.
would be a
Yeah,
long
just
time
it
before you
just
actually
takes time because there's a long way to travel because they're so
long way to
massive.
travel, and there are many. You're transforming photons from high energy ones to low energy ones, and they're scattering many, many times. So by the time they get out to the surface, they've been going for a long time, and then that heat is radiated out. And I think the point that struck me, and it struck other people, it is a topic in astrobiology now. I mean, I looked up afterwards. I was thinking about this independently, but I thought it's actually quite similar to a living entity
Hmm.
establishing homeostasis.
Yeah, we have to
So,
maintain a certain dynamics, and in order to do that, you have to, life creates these gradients and these patterns that
yeah,
involve giving off waste products so that we don't, succumb to disorder ourselves.
yeah. The ordered state of your body is obviously low entropy.
Hmm.
I mean, I don't know if you read Schrodinger's book, What is Life?
I
Have
read it.
you?
I read it many years ago, actually.
I've read it. I've read it about 5 times over the last 6 months. It's full of wisdom and insight, which people should have taken more note of, I must say. But the state of homeostasis that you and I have at the moment is a highly ordered state,
Hmm.
and to maintain that high state of order, we have to ingest low entropy products,
Yes.
food products.
Hmm.
Food products are low entropy products, at least they should be. And we use the food to maintain the low entropy state of homeostasis. And that's a state of, and I think it was Adi Pross in Israel called this a state of dynamic kinetic stability. And he was very careful to point out that this was not a state of equilibrium, it was a state of kinetic stability, which could last for a long time, 100 years for a human if you're lucky.
Yeah.
So you're not rotting, you're not certainly not in thermodynamic equilibrium with your surroundings, but you're maintained in this state of homeostasis. Now, we radiate our entropy through body heat. We only
Hmm.
use typically about 5% of our food to generate useful energy, and the rest comes out as waste heat.
Hmm.
We have to get rid of that basically by radiating it out into outer space. We may do it through stages. We may sweat and use, the heat of evaporation to cool ourselves. We're unusual in doing that, humans. I understand, um, but so we're maintaining a low entropy state. We're radiating entropy away from us to maintain that state. It's a star. It's like a star. It's just
Yeah.
like a star.
Yeah. And
And
stars have,
it's
as I understand it, stars have lifespans and almost like developmental stages as well.
Yes, absolutely. In fact, if you take a star that's more massive than the sun, it will go through many stages of fusing lighter elements into heavier elements. So you fuse hydrogen to helium, you fuse helium to carbon, you generate carbon, nitrogen, oxygen, magnesium, silicon, and so on, all the way up to iron. You can't fuse and get energy beyond iron because iron's the most stable element. So you've lost your capability to fuse when you've got to iron. And so, the universe will end up as iron, in fact, because it's the most stable,
Hmm.
lowest energy state of the periodic table. So if you look at the structure of a high mass star at one time, it will have shells at different temperatures, um, fusing elements between the periodic table, between places in the periodic table. So it's a highly structured object maintained in a highly stable state. And you could call it homeostasis.
Hmm.
It's a long-term
Hmm.
metastable state.
Yeah, it's long
Now,
term.
when
It's
you
maintaining a structure for a long
yeah,
period, not forever, but for as long as
no,
it can.
not forever.
Yeah.
The sun lasts for 10 billion years. The first stars that we're looking at in the universe now are so massive that they'll only last for a few million years.
Hmm.
They go off like flashbulbs. It's very hard to see them because
Hmm.
they just go off like a flashbulb. And
Where in the lifespan of the sun are we right now?
pretty much halfway. The During the evolution of the sun, the luminosity has increased from its initial state to about 20%. So it's a little bit warmer. Well, it's actually not warmer. The surface temperature stays very much the same, but the radius increases due to stellar evolutionary processes. So we have a slightly bigger sun now, which radiates 20% more energy, and that's taken 5 billion years almost. Over the next 5 billion years, it will continue increasing in size until it begins to run out of hydrogen. And, a few billion years from now, it'll start getting more luminous more quickly. And then it will eventually very quickly blow up into a red giant. It will engulf the planets and so on. So we're, a little more than halfway through the lifetime of the star. The luminosity has increased by about 20%, and the planet has coped with that. Not very well at the moment, but the planet has coped with that increase in spectral irradiance from the sun by adapting its atmospheric content and structure and so on. Very James Lovelock, if you
Yeah.
like.
So the atmosphere of the Earth can actually adapt to the output of the sun.
It seems to do, yes, it obviously does. And it's been through rather extreme variations like snowball Earths and so on, where it had low carbon dioxide in the atmosphere and it got very cold. And it could have frozen over completely, but actually it didn't. And there was a process of bringing back the carbon dioxide and allowing it to warm up again. So we've had a not a completely stable state of the Earth during its 4.5 billion years lifetime. In fact, quite big deviations, but it has actually maintained the sort of Goldilocks properties of having liquid water on its surface for all the time.
Hmm. Hmm. How? how much and how has the output of the sun changed over the course of human evolution? So over the course of time since, Homo sapiens was around to today, has there been much change in the output of the sun?
No, it goes through cycles of change, but that's mostly due to the surface structure. The chromosphere and the corona are highly active. We have this 11-year sunspot cycle, and there are variations. There's slight variations in luminosity then, very, very slight. But in terms of the overall billion-year timescale of the sun, there's been very little change over human lifetime.
Okay, so when we think about the history of life on Earth and we talk about things like ice ages and stuff,
Yeah.
that doesn't have so much to do with the output of the sun changing.
Well, there are many contributors to ice ages, and it's not I don't think it's terribly. I'm not an expert, but it's not terribly well understood. There are many things. It's to do with the Earth's orbit. It's to do with variations, small variations in sunlight. If the ellipticity of the orbit changes a little bit, it changes. If the orientation of the Earth's axis changes, which it does, it
Hmm. Hmm.
precesses, that will make changes. So there are many ways of making small changes in the
I
in the
see.
climate.
So it sounds like there's an important distinction to keep in mind when we think about the sun and the earth and life on earth.
Yeah,
There's a difference between the output of the sun per se and
yeah.
what the earth sees based on its tilt and its orbit and all these
And
things.
how much it reflects into space and all
Yep.
of those things. So
Yep.
it's a complicated process. The whole process of getting light through the atmosphere to the surface is quite complicated.
Yeah.
And it
Yeah.
obviously depends on latitude, it depends on variations in climate and so on. So
Yeah.
yes.
So
But
given,
I think the point that I wanted to make there was there's something there which is very closely connected to life on planets
yeah.
like the Earth.
Yeah.
We're so dependent on the sun because it is basically our source of energy. I mean, life has used chemical energy, in the deep vents and in various places. It does use chemical energy as an alternative from sunlight, but basically the life that as we know it on the Earth is driven by sunlight. And what I'm trying to say is there's a closer connection between the sun and the Earth than perhaps we've realized until very recently.
Yeah.
I will explain to you a little bit later on. I'll explain there's an incredible congruence between the radiation that's emitted from the sun and the radiation that life needs in order to metabolize properly.
Yeah. Yeah.
And this,
Yeah. I,
this is obviously an evolutionary adaptation, but it hasn't been, I think possibly I'm the first person to realize this close congruence because I'm an astrophysicist and I know a bit more about the nature of the solar atmosphere and how it works. But there is an incredible numerical and congruence between the requirements of life,
mhm.
as we know from metabolic theory,
Yeah.
and the output from the sun. It's much closer than you might have imagined.
Yeah. Yeah. And I suppose you're starting to say that it's not a coincidence.
I'm convinced it's not a coincidence. I mean, this is not public knowledge yet. I mean, this is very new.
Yeah.
These are
Yeah.
very new ideas that are coming out.
Yeah.
But
With that in
uh,
mind, I mean, can you say a little bit about how does the light coming off the sun, how does the light the sun is emitting compare to what is actually touching our bodies here on Earth? What's sort of getting filtered and stuff, but by the
well,
time it
let's
gets here?
okay. Well, let's kind of follow a photon from the surface of the sun. We get a
Mhm.
photon coming out of the sun, and the photons of different colors will actually originate at some slightly different depths within the atmosphere. And it turns out that the near infrared photons come from deeper in the atmosphere of the
Mm.
sun than any other color of photons. And that's very relevant, and I'll explain that a little bit later. But so the photon coming from the sun, when it reaches the atmosphere, when it reaches the top of the atmosphere, it has to traverse the atmosphere, and that's a process which can be very well modeled. I have a model myself, which I use to model that process. But the two physical processes that are relevant to to the light photons getting through the atmosphere are first of all scattering. that's bouncing the photon from a molecule in the atmosphere or an aerosol, it could be bigger than a molecule. So there's Rayleigh scattering and aerosol scattering. And there's also absorption. So gases in the atmosphere will absorb light at some wavelengths.
Mhm.
Now, it turns out that in the visible part of the spectrum, there are very few absorbers and they're very weak. So there's actually very little absorption of sunlight in the visible spectrum coming through the atmosphere. The dominant process is scattering. It's entirely dominant in the visible. And scattering, of course, is what makes the blue sky. It makes the white clouds and the grey clouds and so on. So when a photon travels through the atmosphere, most photons get straight through. Most photons will get straight through to the surface, but some of them will get scattered to make the blue sky. Some of them will get scattered by aerosols and water droplets in clouds, and some of those will eventually end up on the ground. Some of them will end up going back into outer space. But there's rather little absorption of photons in the visible spectrum. We lose very little from absorption in the visible. The absorptions are very interesting. Some are due to water, some are due to oxygen. There are a few pollutants that absorb in the atmosphere, like nitrogen dioxide. Um, but the absorptions are generally rather weak. That changes when you get to longer wavelengths and shorter wavelengths. If you go into the ultraviolet, then you get ozone absorption, which is what protects us from the ultraviolet damage from the sun. So the ozone below about 300 nanometers, the short wavelength cutoff of the atmospheric transmission, is completely absorbed by ozone. At around 300 nanometers, we get this very, very tiny window where there's enough ultraviolet radiation to generate vitamin D.
Mhm.
We can generate vitamin D up only to about 320 nanometers. So we
Mhm.
get this tiny window of between, 300 and 320 nanometers where we can actually generate vitamin D. That's also a very long and interesting story that I don't know that we'll have time to get into. But interestingly, you have to realize you don't only get this radiation, this ultraviolet radiation, directly from the sun through the atmosphere. You also get it indirectly by scattering from the upper atmosphere and down vertically through the ozone layer.
Yeah.
So you get a significant fraction of your ultraviolet vitamin D producing ultraviolet radiation indirectly, even in the winter. It's often said that if you're in the winter, you can't get any vitamin D because the sun's too low in the sky. Well, it's not exactly true. I mean, you get less vitamin D, certainly because you don't get it directly from the sun, unless the sun's above about 30 to 40 degrees. But when the sun is at 30 or 40 degrees, it's shining into the upper atmosphere as well.
Mm.
It doesn't have to take this long tangential path through the ozone layer where it all gets absorbed. It can scatter from above
Hmm.
the ozone layer down vertically through the ozone layer and reach you directly. So
Okay,
it's a
so
significant,
the angle is such that the light coming directly from the sun has to go further, but it can be at the right angle that it's going directly into the
yeah,
upper atmosphere and getting bounced back
yeah.
down.
The ozone layer is between about 12 and 40 kilometers above the Earth. We don't have very much ozone at the ground level, fortunately. We get some, but not very much. But most of the ozone is about 12 to 15, 20 kilometers above the surface of the Earth. And so if the sun is very low, it travels in a slanting path through the ozone layer, and that will absorb all the ultraviolet below 300 nanometers and a bit beyond. So it's a myth that you can't get any vitamin D from the sun in the winter. The
Hmm.
reason you don't get it in the winter is you dress up in clothes which block the UV. It's not because you don't get it from the sun. And it's not widely realized.
Yeah,
It's
yeah,
well
yeah.
documented, but it's
So
not widely realized by
yeah,
people.
the
And in
primary
fact,
reason that people don't get vitamin D synthesis when they go outside in the wintertime is
yeah,
that they've covered their entire body in stuff that will block the
yes,
light, not that
exactly,
they cannot
exactly.
possibly get it from the light.
Yes. And in fact, Scandinavians, often I have friends who do this, often go sea ice skating in the winter. and they get very warm. So they do this in t-shirts, and they actually get plenty of vitamin D in the winter
Wow.
from doing that. But
Wow.
if you're dressed up in fully clothed and so on, you're cold. You don't.
Wow. I mean, that makes sense now that you say it like that, but wow, I had no idea that was true.
No, people don't. And you can I model this quite easily. You can see that you can get quite a lot of scattering from the atmosphere, which will give you. And this is why you can get quite badly sunburned even under an
Right,
overcast
right.
sky, because the clouds will also scatter UV very effectively. So you've got to be careful. It's not just coming from the sun.
Interesting. I
Anyway,
want to
so
I want to turn now to what you mentioned earlier, Schrodinger's book, What is Life? Can you set
yes,
this up for us? So this was a book written in the earlier parts of the 20th century, and this was at a time in the history of science where you sort of had physicists starting to now think about biology and the question of
yeah.
what life actually is from a physics perspective. So what was that book all about, and what was he actually saying there?
Well, it's an extraordinary story. I mean, Schrödinger was an anti-Nazi, so he was expelled from Germany early on. I think he left Germany in the early 30s to live in Austria, and so he lived in Austria. His mother was actually English, and he lived in Austria until it became impossible to live in Austria. And he was invited by the Irish government. I think he was invited by de Valera to come to Dublin and set up an Institute for Advanced Study in Dublin. And so he came over and did this. And it was while he was in Dublin, he was giving lectures on biology, on what is life. And that's when he wrote the book. And it's written in extremely good English because he spoke English very well. And there are insights into that book, inside that book, which I think are absolutely stunning. And there's a relatively modern edition of the book, 19, I think it was 1991 or 1992, which had a and it not where I put it now. Anyway, it had a written in 1992. It had a foreword written by Roger Penrose. Roger Penrose, very
Yes,
well-known
yes.
mathematician. He was the guy who was Stephen Hawking's thesis examiner. Very brilliant mathematician, and he wrote a foreword to this book. And actually, the quickest way I can explain this is to actually read his foreword to you.
Yeah, yeah, let's do it.
It's less than a page long, and I'll read it to you. And it's a great inspiration, I have to say. And this is Roger Penrose, written in 1991. He said, "When I was a young mathematics student in the early 1950s, I did not read a great deal, but what I did read, at least if I completed the book, was usually by Erwin Schrödinger. I always found his writing to be compelling, and there was an excitement of discovery with the prospect of gaining some genuinely new understanding about the mysterious world in which we live. None of his writings possess more of this quality than his short classic, What is Life, which, as I now realize, must surely rank amongst the most influential of scientific writings in this century. It represents a powerful attempt to comprehend some of the genuine mysteries of life, made by a physicist whose own deep insights had done so much to change the way that we understand what the world is made of. The book's cross-disciplinary sweep was unusual for its time, yet it's written with an endearing, if perhaps disarming modesty, at a level that makes it accessible to non-specialists and to the young who might aspire to be scientists. Indeed, many scientists who've made fundamental contributions to biology, such as JBS Haldane and Francis Crick, have admitted to being strongly influenced by, in brackets, although not always in complete agreement with, the broad-ranging ideas put forward here by this highly original and profoundly thoughtful physicist. Like so many works that have had a great impact on human thinking, it makes points that, once they're grasped, have a ring of almost self-evident truth, yet they are still blindly ignored by a disconcertingly large proportion of people who should know better.
Hmm.
How often do we still hear that quantum effects can have little relevance in the study of biology, or even that we eat food in order to gain energy? This serves to emphasize the continuing relevance of Schrödinger's What is Life has for us today. It is amply worth rereading. Now,
Hmm.
I think that's a wonderful bit of text
Yeah,
for
it
an
was.
advertising a book.
Yeah. I mean, one of the things that comes up there for me immediately is, that little bit about things that are, he basically said there's things that are clearly true that people pretend aren't true. And I can remember all throughout my education, and I studied
Mm.
biology primarily, not
Yeah.
physics, but I remember over and over again hearing from very famous, very
Mm.
illustrious biologists quantum effects are completely irrelevant. They happen at a small scale. It just period end of
Yes.
discussion. And it was just sort of
Yes.
stated as a fact.
I think this has had a profound influence on biology, and I think there's a very rapid transition going on at the moment, and it's being driven by a younger generation because
Mhm.
the older generation of biologists, don't know about quantum
Yeah.
biology at all,
Yeah.
and
Science progresses one funeral at a time.
yes, but it's so deeply embedded. This quantum idea is so deeply embedded in biology that it has such a profound impact on the way we understand what is life. I mean, it was a wonderful title for a book. He asked the
Yeah.
question, he got closer to understanding what his life is than anyone else
Mhm.
had, I think.
Can you
And this
sketch?
idea of this
Can you sketch?
idea of ingesting order,
Yeah.
low entropy nutrients is absolutely the key to what we are, I think.
Yeah, yeah. And as I understand it, right, when he approached this question as a physicist, it was okay, well, the laws of thermodynamics clearly tell us that entropy should increase over time,
Mm.
things should become more disordered, and yet living things seem to defy this. So, in
Yes.
some sense, you have to explain how life defies the laws of thermodynamics, seemingly.
Yeah. And you just have to add the phrase in a closed system. Very commonly used phrase by people who work in thermodynamics. Yes. I mean, life, as is the interior of a star, is a low entropy unit in high entropy surroundings. So why is the universe doing this? I mean, this is the question in my mind.
Mhm.
What is it about our universe that it, lets it enables it to defy a fundamental law of nature, the second law of thermodynamics. It's not defying it, of course. It's
Right, right.
only a misconception, but it creates low entropy regions in a high entropy
Mhm.
environment,
At very different
and
scales as well. As well.
and different scales. There's the star on one side, and the star. Look at biological evolution. What's the product of biological evolution? It's complexity. It's
Mhm.
using time as a resource in order to generate increasing amounts of complexity using molecules,
Yes.
biomolecules,
Yeah.
basically.
Yeah, and another, this I think connects into another what I would call misconception in biology that I was always taught, which is that evolution has no general direction. Now, there's a random quality to evolution, but a steady trend over evolutionary history of life on Earth is an increase in complexity,
Yes,
and that has
exactly.
steadily and I mean, I don't know if I want to say the word predictably happened over time, but it has moved in that direction clearly.
Exactly. And this is go back to the star for the moment. Now, in a biological system, you're developing biological complexity. You're developing, biological engine structures which can perform functions more and more effectively, and it gets more complex as you go downstream in time. What's the star doing? The star is exporting entropy, but it's also producing complexity because it's the stars that are producing the periodic table.
Hmm.
Now, the periodic table of elements is much more complicated than hydrogen and helium,
Mhm.
and that complexity is pregnant with future complexity because
Right, right.
it's those elements in the periodic table that are being used to make biomolecules, to make life, to increase complexity at a different scale, different time scale, different scale, in a very, very similar system. Now, I'm not saying that stars are alive, but the comparison between a star and a life form is very, very close.
Yeah.
in terms of basic physics, the entropy gradients and the export of energy and the production of complexity and so on. They're very, very similar. So I think this is an idea that in biology, I think is going to be very
Hmm.
productive
Hmm.
because we can then realize that, if we're dependent on starlight to drive the process of life on the planet, it'll be all of the starlight which is used, all of the starlight that's accessible to the biosphere will perform its function in producing more and more complexity. And the complexity at the moment has reached the level of cognition, the fact that we're talking about it. So, the waste product from the sun has been used as a driver for complexity in a biological process on a planet in the Goldilocks zone to produce increasing complexity up to the level of cognition. And so we have, first of all, the chemical elements, complexity from stars,
Yep.
and now cognition, which is a complex product coming from life, fed by starlight
Yeah.
on the Earth.
Yeah.
It all fits together, in a much more a big picture way. It
Hmm.
all suddenly seems to come together. And when I tell you about the close connection between the sun and the biology, I think you'll get it.
Yeah. Yeah. So we've got an analogy here between something like a star and something like a
Yeah.
living being. You've got a low entropy core structure that is surrounded by or embedded in a higher entropy environment. And
Mm.
somehow the way all of that stuff works starts to result in increased complexity. Stars
Yeah.
start yielding over the course of the universe, they start yielding more and more of the periodic table of elements.
Yeah.
Eventually, some of those components of the periodic table of elements can come together in a way that gives us life, which of course
Mm.
starts out as simple single-celled
Mm.
prokaryotic life. Eventually you get eukaryotes,
Mm.
multicellularity, you get more complex multicellularity, and then eventually you get minds and
Mm.
you get cognition. So there's this connection between complexification over time
Yes.
resulting from this lower entropy core structure that gets
Yes.
created that's surrounded by a higher entropy environment.
Yeah. Um, there's somebody called Sean Carroll. There are two Sean Carrolls. One's a
Yeah,
biologist and
I
one's an
actually did
astrophysicist.
my college training with the biologist
Well,
Carol.
the astrophysicist at Caltech, Sean Carroll, I know him, I've met him, and he's a very good pal of a colleague of mine. Um, he gives lectures about cosmology and particle physics and so on, and he has this very nice demonstration of the relationship between complexity and entropy, which I'll try and explain to you.
Mm-hmm.
It's actually quite straightforward. But it raises the question that, we've not yet learned how to quantify complexity. I mean, we can quantify entropy. We know what entropy is, although it's a slightly confusing topic, but we know it can be quantified. But complexity at the moment is not quantified. It certainly has something to do with information and so on. Um, but his example of complexity and entropy is to take a cup of coffee, which has the black coffee at the bottom, and you very carefully poured cream on the top.
Mm-hmm.
So you have a perfect separation between the cream and the coffee. And he would describe that as a low entropy state because you can describe it in one sentence. You say, I've got a cup of coffee, it's all coffee on the bottom, it's all cream on the top. QED, that's it. That's all you need. If you leave that cup of coffee, it'll start mixing and it'll start generating swirls of turbulence and so on. And if you describe its complexity during the process while it's mixing, the complexity increases
Mm-hmm.
up to some level
Right.
where you get a very complex structure. You could look at it macroscopically and you can see all these different swirls
Yeah. Yeah.
and so
Yeah.
on going on. And then, as time goes on, it will just become completely mixed. And you'll end up with a perfectly mixed cup of cream and coffee, which is a, a high entropy state,
Mm-hmm.
but it's at very low complexity. So the entropy rises continuously as you're letting this coffee evolve, but the complexity goes up to a peak and then drops down again.
Yep.
And this is what's happening in the universe at the
Yes.
moment. The peak complexity, I think we've already passed, in some sense, in stellar processes, we've passed the peak complexity because the star formation rate peaked about 10 billion
Hmm.
years ago
Hmm.
at high redshift, redshift of about 2 or 3 or 4. And since that time, the rate of star formation has been dropping, and it's much
Hmm.
lower now than it was at that time. So we're already in the
Hmm.
aging tail of the universe, where the universe was much more exciting about 10 billion years
Uh,
ago than it is now.
so from a complexity
But
standpoint, at the stellar level, the universe is past its prime.
past its prime, yeah.
And so
But
that would
but
imply,
on the other hand, we're now making complexity in a different way, and so
yes. Well, yeah.
it's in some sense
If
taking over.
if I put what you just said together with just common sense observations in the flesh and blood world and the technological world that we inhabit, that would imply we're clearly getting more complex because now humans, with all their complexity, are starting to create things that we think are more complex than ourselves. But if I put these ideas together, if the complexity of the universe at a stellar level has peaked and it will then go down, that implies the same thing will happen for us, the realm of living things. And the question would be, are we at or not yet to that peak in complexity?
I'm sure we're not at it. I mean, this is we're looking very far into the future, and I mean, in terms of the universe, we're looking very far in the future. We're looking at many, 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 many tens, hundreds, thousands, billions of years. I mean, that's a long time in the future. I mean, the star formation rate has decreased. It certainly hasn't decreased to zero. There's lots of star formation going on.
Mm-hmm, mm-hmm,
And meanwhile, of course, the universe is richer in these heavier elements, which are pregnant with further complexity. So we're nowhere near the end yet. But it is an evolving process, and I think this idea that there's a relationship between complexity, which comes to a peak, and entropy, which continues increasing, is rather fundamental, I think.
mm-hmm.
So we probably don't want to go too far down this route. Certainly not get to black holes because then it get much more complicated. But I think the main point I wanted to make is there is this very close connection between an organization of a star and the organization of a living body, and
Yeah.
they're sharing resources in some way. We're sharing resources. We're passing resources down from one level to the next.
Mm-hmm,
The
mm-hmm,
sun is passing not only its light, it's passing on the chemicals it's made to something which can become life. And
mm-hmm.
so, and perhaps that's another point I can make about the nature of life on Earth, which I think is not often made. And it fits into the story here in a curious kind of way. But if we look at the environment of life around us, we're surrounded, if we're lucky, by vegetation. And of course, the vegetation is extremely important because it does the photosynthesis, which makes our food that we eat to live, and so on. So plants are absolutely fundamental to the process. If you look at the way light interacts with plants, it uses the higher energy visible photons to split water and perform photosynthesis. So it's the photon energy coming from the sun, the visible photons coming from the sun, that are actually converted by photosynthetic process to the sugars. So you're directly converting um, photon energy to chemical energy via the photosynthetic mechanism. And
Mm-hmm.
then that chemical energy is what animals and fungi use and so on to do their stuff. Um, but it's also true, and you can observe this very easily if you can see in the infrared, that the sunlight uh, interacting with the plants above what we call the chlorophyll red edge at 700 nanometers, where chlorophyll becomes transparent, that light is very quickly and effectively re-radiated by the plants.
Mm-hmm.
So you take infrared photographs of trees and vegetation, and the leaves are white, bright white, because they reflect incredibly
Mm-hmm.
well.
So that means when you're
And
outside in a in a shady area with lots of green vegetation around, it's actually
Yeah,
reflecting that longer wavelength light back at
exactly.
you.
So, and then if you put yourself in the forest understory and you look at the light around you within the forest understory, I've made these measurements with my spectrometer. It's remarkable that you're incredibly rich in this infrared light, and you're because the understory can be quite dark. The ratio between the infrared light level you're getting and the visible light you're getting can be many tens. It can be over 100
Mhm.
in a dark understory. And so if you're living in the understory, you're bathed in an extremely strong infrared radiation. And I think this is very pertinent to the evolution of life. There's a very recent paper in the biological world which looks at the longevity of mammals that live in arboreal regions and comparing them with similar size scale of mammals that are living in the open savannas and so
Hmm.
on. And the animals that live in the understory live longer,
Hmm.
statistically very significantly live longer than the animals in the open
I would imagine
areas.
that's when you control for things like body size.
Yeah, in fact, it fits into the metabolic theory of ecology,
Mm,
which we'll come to in a moment, perhaps. But yeah, it fits into the scaling laws of yeah. And in fact, it's a perfect parallel line in those scaling laws, but significantly shifted to longer lifetime.
right, right,
And
right.
the argument in the paper is this is due to lower predation in the forest, but I don't think that's true at all.
You
I
think it
think
might?
it's increased metabolism, better
I see.
mitochondrial function.
Okay, and that's going to be the connection there between longer wavelength length light and mitochondrial function. I think we're going to come to
Yes,
that. Before we get
yes,
into some of that stuff, I just want to ask you one more question about Schrödinger. That in his famous book, What is Life? You said you've read it several times, and there's
yeah.
some stuff in there that's underappreciated. What's in there that you find compelling and insightful that people seem to miss?
Well, I think the dominant factor there, and he admits it in the book. He only wrote the book to write chapter 6, which was about entropy.
Hmm.
And what he pushed was the idea of negative entropy. It was strongly reacted against by physicists who said you can't make negative entropy. And he said, all I'm talking about is order. Order is negative entropy, and with some reference. So chapter 6 in the book is the real guts of what he's saying. And he's saying we're not eating, we don't eat to get energy. That's a byproduct. We eat to maintain the order in our bodies. We eat to keep ourselves alive. We're eating in order to keep our homeostasis generating mechanisms operating. Now we need energy to do that, but we have to export the waste, a lot of waste energy by doing that. And so we have to export entropy and waste heat and so on. But we're actually eating to create order and to maintain order in our bodies. And there's a thought here, and I had this thought some while ago, and I tried it out, and I've not heard it repeated. But if there's a huge debate about ultra processed foods at the
Hmm.
moment.
Hmm.
And I'll admit that in feeding yourselves ultra processed food is not going to be good for you. It's going to be and it's very closely related to the infrared light, which for reasons I'll explain. But what is ultra processed food? Ultra processed food is chemicals that you find in foods, possibly made in factories, possibly um, extracted from food processes and refined to the extent that it's just molecules, chemical molecules. And those chemical molecules are, stirred together and cooked and made into food. Now, I would call an ultra-processed food made in that simplistic way of pure chemicals is maximum entropy food. It has the maximum entropy that you can generate with a mix of those molecules, because they're all just mixed together. There's no structure in there. There's no cellular structure. There are no amino acids. There are no, there are no higher chemicals which you might get from your digestive tract. You'll extract complex structures from your digestive tract, and you'll use those complex structures as a nutrient to maintain
Yeah.
your body
If I eat a piece of steak, I'm getting all of that higher order polypeptide
structure.
protein structure. But if I have
Yeah.
protein powder, it's just individual amino acids.
So I would say, I'm saying this with my tongue in my cheek to some extent, but I would say an ultra processed food has essentially no nutritional value in the sense of importing order into your body. It's essentially useless.
Hmm.
Now, I'm sure I'll get shot down for that by whoever wants to argue about it. But if you think of it, you cannot make you could not make the ingredients of an ultra processed food any more disordered than it is. And so it contains no structure, it contains no order, it contains nothing to help you maintain your homeostasis. This is why it gets shipped aside to make fat. It doesn't get used very effectively to make energy. And, I think if you could put a label on food saying, what's its entropy value, you could say for ultra processed food, it's maximum entropy. It couldn't be more mixed and useless than it is.
You're saying that potentially the ultimate and what you might call nutrition fact would be the entropy of a food.
Yeah. Well, actually, that's what Schrödinger was arguing. Exactly what he was arguing.
Hmm.
It's the entropy. You can eat high energy content foods
Mm-hmm.
which have structure and are absorbed in your gut at the right place at the
Mm-hmm.
right time, which will be extremely
Mm-hmm.
beneficial. If you eat this very high entropy
Yeah.
food, I'm not a nutritionist, so don't,
Yeah. Yeah.
listen too carefully to what I say, but it doesn't get digested in the right place and it doesn't contain any order.
Mm. Yeah. So let me get your take as a physicist on the following thing. This is a kind of debate that you see out there in the diet nutrition world. So when we think about the relationship between order and
Mhm.
structure and energy and waste production, right? So
Mhm.
the sun is producing light as waste. We produce our own waste as a byproduct
Mhm.
of our metabolism. When you think about the relationship between waste production and order and the maintenance of
Mhm.
order, how would you start to interpret someone who is say has higher body heat and is in a hypermetabolic state versus someone who's in a more hypometabolic state with a lower body temperature? If we're producing heat as a byproduct of our metabolism and the production of that waste as heat is
Mhm.
necessary for us to maintain homeostasis and our order as a living thing,
Mhm.
how would you interpret someone with, say, a higher body temperature versus lower body temperature in terms of how ordered they are?
Yes, I mean, I think it's a difficult question for me to answer, not being a biologist or a medic. But I will say that, I think it's well known now that if you have a fever, it increases your body temperature, and that enables you to um, beat the cause of the fever. So the fever is a valuable thing in order for you to maintain your homeostasis properly. And I think. It actually comes back to the other thing. I'm not avoiding the question. I'm going to answer it in perhaps a slightly different way.
Mm-hmm.
The other thing in Schrödinger's book is that he argues that when he's talking about the stability of DNA, it's another important chapter in his book. He's saying that um, in order to have a low enough mutation rate, you have to have a high enough energy barrier to stop molecules just mutating too quickly. And, the working temperature of your body, you don't want to have a high enough temperature that you can actually move atoms around within molecules
Mm-hmm.
because you don't want to induce mutations. So he uses the basically the Boltzmann-Arrhenius equation, an energy barrier divided by e to the energy barrier over kT. He uses that as a way of measuring mutation rate. So it's what he says is the inverse of um, the rate of metabolism, for instance, where if you have a low energy barrier in this equation, you can metabolize quickly. If you have a high barrier, you metabolize slowly. Perhaps I'm not explaining this very clearly, but I think the point is that I mean I'm coming to this point when I'm explaining the relationship to the sunlight,
Hmm.
and that is that if you I don't know I mean as a biologist you must have learnt about the metabolic theory and the scaling rate laws
Yes,
between
yes. In fact, I
size
had
and
an early,
longevity and temperature
yeah,
and so on.
an early episode that I'll refer people to because it might be a good one to follow up if you listen to
Yeah.
this one, is with Jeffrey West.
Oh, you've actually got an interview with him. I didn't
Yes,
realize
yes.
that. Yes, he was the founder of this, wasn't
Yeah,
he?
so I read his book years ago, but could you give us just a short, concise summary of what we're talking about here? How things like
Well,
metabolism and longevity scale with body size?
what I'm getting to is that if you look at this metabolic theory and look at the data from all the animals of different sizes and so on, there's a common energy barrier in
Yep.
there called the redox potential. There's a common redox potential for all of life, which has a mean value of 0.66. I think the current value 0.66 electron volts. And this seems to be a common fact of life over, many orders of magnitude in scale size. All of life has this is this barrier, and this is this Boltzmann-Arrhenius equation. It's
Hmm.
e to the minus 0.66 electron volts over kT or RT, whichever way you're doing it. Um, and so that redox barrier is what stops our body just performing chemical
Hmm.
reactions willy-nilly.
Yeah. Basically,
There
I
is a
think
barrier to biochemical reactions
is the
which
idea here that
allows us to control it.
yeah, the idea here is that past this barrier, you wouldn't be able to maintain the low entropy state of life.
Yeah, I mean, it would all happen, and you'd all dissolve into a sludge. And so you need these barriers to maintain control over your metabolism.
Hmm.
And these barriers, a good example of these barriers is down the electron transport chain in the
Yes.
mitochondria,
Hmm.
where you get a total change in voltage of about 1.1 volts down the chain, but it's divided into. It's not done all at once. It's done in through different complexes. So
Yes.
it's done in pieces. And this is, of course, very clever in a mitochondrion because you avoid doing too much damage by doing it in small bits. But you can still do it fast enough in order to maintain your ATP production and so on.
Yeah. Yeah. And
So
when
the
you
fact is that all of life, the metabolism of all of life, has this mean value of 0.66 electron volts, and this is where we get the maximum number of photons from sunlight.
hmm. Explain
So,
that now. What exactly does that mean?
well, if you look at a normal plot of the solar spectrum, it'll be plotted as something like watts per square meter per nanometer per unit wavelength. And it peaks in the visible and it drops down and tails off into the infrared. Very familiar diagram of the solar irradiance spectrum. And the peak in the infrared is where you get most of the energy from the sun. But you actually get most of the photons in the infrared, of course. Um, but that's one way of plotting the solar irradiance spectrum. You can transform that into different units and different representations, which are much more appropriate for biology. And that's the representation which is used by the people who design solar panels. They're interested in using sunlight, photons of sunlight, to generate electrons to harvest in solar panels. And that's exactly what we're doing in life. We're using solar photons to move electrons
Yeah.
in the electron transport chain for folding protons, for folding proteins, for doing all kinds of things. We need energy to move electrons around within a living system. I mean, if you read Nick Lane's books about the mitochondrion, he goes into glorious detail about moving an electron from one place in the Krebs cycle to another place. And these electrons have to overcome these barriers in order to move.
Yeah.
where do they get their energy from to get across the barriers? Now, I think the biologists would generally say, if I've got to get over a redox barrier to make a chemical reaction, I'll use an enzyme, and it'll lower the barrier, and I can get through it. It's used all the time in life. We're full of enzymes. Another way to do it is with quantum tunneling.
Hmm. What is that? What is
Uh,
that?
Quantum tunneling is when you have a barrier that you have to get over. So if you imagine you're coming down a hill, and instead of going rolling straight down the hill, you've got a little hill that you've got to get over
Hmm.
before you continue down the big hill. And this is like the electron transport chain. You're coming down the electron transport chain. You have a barrier at one of the complexes, which you have to get over. And in some cases, you use an enzyme to make the barrier a bit lower. In the complexes, you use an enzyme. But in other places in the electron transport chain, you actually have to use quantum tunneling. And that's where if the barrier is very small in size, about a nanometer in size, if you have an electron of around about an electron volt, you can quantum tunnel through that barrier with some probability, and a significant probability. If your barrier is 1 nanometer and your electron is 1 electron volt energy, uh, the wavelength of that electron, the de Broglie wavelength of that electron, is 1 nanometer. So you get a very significant probability of tunneling through that
Hmm.
barrier. And I think this is very important for us living in the dark, because we need to metabolize in the dark. But where do we get the energy from getting over all these barriers that we need to get over? We get some from the high velocity end of the Maxwell Boltzmann distribution, the Boltzmann-Maxwell distribution. There are a few particles that are moving around at our body temperature, which can provide enough energy to do that. But it doesn't allow you to metabolize very quickly. And so this is the point, that in order to get over that average half an electron volt barrier, you're going to need either an enzyme, you're going to need to wait around for quantum tunneling to allow you to do it, or you're going to need an energy source. And I think the idea that we're working on at the moment is that energy source, which is abundant to us during the daytime, is infrared photons.
Hmm.
Because these infrared photons coming from the sun have energies, between a few tenths and a couple of electron volts. And they're perfect for providing the energy to get over these barriers. So they
Hmm.
can speed up the movement of electrons during the daytime. And the question is, and the question that's occupying us, how actually does this happen? What is the link between the solar photon that has, say, an electron volt or half an electron volt of energy? How do you transfer that electron into the electron transport chain and make the electron get down the chain to
Mhm.
produce ATP? And so we're pondering that. We're talking about it in this group of quantum biologists in the Guy Foundation. Have you come across the Guy Foundation?
No, no, no.
Well, it's a private foundation in the UK, funded by an ex-medic and big pharma company owner. He funds an organization of quantum biologists around the world. It's international. We have meetings from all around the world every couple of months and every couple of weeks. And so we're discussing the mechanisms by which the photons coming from sunlight can actually interact directly with the mitochondria. And I mean, I can talk you through that in a little bit more detail. But at the moment, what I want to say is that if you come back to the people who are building solar panels
Mhm.
and look at the way they plot the solar irradiance, they generally plot it, because they're dealing with amps, they're dealing with current, they plot it as energy, photon flux, the number of photons per second per unit area, per unit energy, rather than power per square meter per nanometer. They're plotting it as photon flux because it's photons that are doing the work. It's not the power that's doing the work, it's the individual photons that are doing the work. So if you plot the solar spectrum in these units as photon flux per unit area per electron volt, the sun looks quite different. It has a very sharp peak, like a mountain, at 1600 nanometers,
Hmm.
which is which is due to the properties of the solar atmosphere, and I'll explain that in a moment. But
And
the
that's near
maximum,
infrared light?
it's near infrared. Well, it's near infrared, 1.6 nanometers. It's a broad peak, very broad peak, extends right down through the visible and extends out to long wavelengths. But the peak is at 1.6, which is 0.75 electron volts, which is very close to 0.66.
Right. It's just above it.
It's yeah, but I mean, they're both very broad distributions, so
Hmm.
it's essentially
Hmm.
identical. And when I saw this number, I thought, there's something very special
Hmm.
going on here
This was
in
that
biology.
redox energy barrier you were talking about a little bit ago.
This is the redox energy barrier, and if you look at the output from the sun, uh, it peaks at that wavelength, broad distribution. It peaks in photon number, and if you integrate that over the range which is relevant to the redox reaction, say from a few tenths of an electron volt out to about 1.5 electron volt, you're getting about 10 to the 22 photons per second getting to ground level from the sun in that range of
Mhm.
energy,
Mhm.
10 to
So
22
so
per
if I'm following,
second.
so the peak photon flux per unit energy from the sun that you measure here on Earth
Yes.
is in the near infrared part of the spectrum.
Yeah, exactly. In fact, I can show you. I mean, I know this is not a video podcast, is
Oh
it?
yeah,
But
it'll be partially video, but
oh,
we'll
it's partially
describe what we
video.
see here. Yeah.
But I can certainly show it to you very easily. And yeah, hang on just a moment. Actually, can I share my screen? And,
Yeah. Go for it.
if you let me share my screen, then I'll probably do it more easily.
let's see here. Share screen options. You should be able to do it now.
Okay. Okay, let me go to. I'll just have to go up and open the file up.
So we'll do our best to describe what we're looking at here, folks.
Yeah, but
For
I
those,
want I want you to see it because I think it's
yeah.
it's very important. I'm going to have to stop sharing for a moment and share again because I
Okay.
should have it open in another window now. Yeah, here we go.
Okay. Yeah, here we come. All right.
Okay,
Yes, I can see.
you've got that. Okay, so this is plotted against
Yeah.
wavelength. They often do it against EV,
Yeah.
but
This is what you were just describing to us verbally.
this is what I was just describing. So down at the left-hand end, we get the visible light, and you can see where photosynthesis happens. The black line is the sun above the atmosphere, and the fainter green line is the light that reaches the ground with
Hmm.
an air mass of 1.5. It's the standard way of doing it. Now, this red line is the Planck function at the effective temperature of the sun, which is 5780 kelvins. Okay, and you see this big excess in the near infrared. You can just about see this in the normal plots, where if you look into the infrared, you'll see that the sun exceeds the Planck function slightly
Mhm.
in the
Yeah.
infrared.
Am I
And
right to say that it's as if the Earth is magnifying that part of the solar output?
no, it's not. It's a property of the solar atmosphere. It's simply the
Okay.
fact that in solar type stars, that is, stars which are relatively cool, i.e., not in very hot stars at 10s, 15,000 degrees, 15,000 kelvins, not very hot stars. In the solar type stars, the electrons in the atmosphere come from what we call the metals, all the heavy elements. We can't get electrons from hydrogen because there's not enough energy in the atmosphere to ionize hydrogen. You have to go to much hotter stars to ionize hydrogen in the atmosphere. So you get a solar atmosphere which has lots of free electrons, but they all come from the metals. And those electrons can pair with hydrogen atoms to form what's called an H minus ion. This is all very well known astrophysics. It's the first thing you learn when you do stellar astrophysics. Okay, and
Hmm.
I apologize it for because the biologists will never have done this, but you can generate these negative hydrogen ions in the in the atmosphere, and they're the dominant source of opacity in the visual spectrum of the sun. And they have that opacity has a minimum value where you actually disassociate the ion, and you can knock the electron off the ion with three quarters of an electron volt, 0.75 electron
Hmm.
volts.
Hmm.
And that produces a minimum cloudiness or mistiness in the solar atmosphere, which means that the light that comes to you from those wavelengths is coming from deeper in the atmosphere where it's hotter. So the sun doesn't emit a perfect Planck spectrum. It's hotter in the near infrared because of this minimum opacity in the near infrared.
Okay. So it
And
is the output of the sun.
the output of the sun is higher
Yeah.
by a fairly significant amount spread over wavelengths, as you can see. And this is the wavelength within which light can penetrate the body.
Yes.
And it seemed to me that the coincidence between the action potential that you need for all of life and this excess energy coming from the sun is likely to have driven the evolution of life
Yes.
for 4 billion years on the
Yeah.
planet
It,
to
it
bring
sounds like yeah.
these two into coincidence.
Yeah, it sounds like what you're saying is this is not a coincidence. Life probably adapted to this pattern of solar
Yes,
output, and that
yes,
is why near infrared light does all of the things that it does that we might start talking about next.
exactly. Yes, it's not infrared light is not useless for life. It's a
Right.
fundamental part of allowing life to metabolize properly. In fact, we are willing to coin the term photometabolism to
Hmm.
describe this process. It's
Hmm.
a
Hmm.
and it's the thing is, before biologists erupt in disgust, we say the photosynthesis is different. The photosynthesis
Right.
is using solar photons as a source of energy.
Right.
It's converting those solar photons into chemical energy. We're not doing that here. We're using the solar photons to catalyze a process of burning
Yes. Yes.
that food.
Yeah.
So
That's
it's a
so.
catalyst. It's a
Yes.
photocatalyst for metabolism.
Yeah, I'm glad you brought that up. So, yeah, I wanted to start to come to this. So, you're not saying that we, animals are doing photosynthesis like plants do, but you
No,
are saying that all life is using light from the sun, including near infrared light, which is
yeah,
abundant, to catalyze or modulate how metabolism is happening.
yeah,
And so
exactly.
let's get into that now for animals. We're not talking about plant photosynthesis. We're talking about
Yeah.
mitochondrial metabolism. What do we know about this part of the light spectrum from the sun here, near infrared, infrared, and how it modulates what our mitochondria are doing?
Yes, well, this is the problem we're trying to understand. Let me tell you what we think and what we know and what we don't know. We don't know everything yet.
Mm-hmm.
First of all, we have to get light into the body. If we're going to reach a significant number of mitochondria, it's okay for a fruit fly because the light can get in easily, but in a body, you have to get into the body. Now, how do you get light into the body? Most people would say light penetrates very small distances in the body, and indeed in the visible, light does penetrate only to this layer of the skin, essentially. It
Can you
goes
do
a
stop
little
the
bit
screen
deep.
share?
Yeah, it goes. Yeah, I'll get rid of the screenshot. Okay, you've seen that diagram. Stop share.
Okay.
So the thinking is that in the visible, you only penetrate to very shallow depths
Mm-hmm.
because you have such strong chromophores. You have strong pigments all through the visible. You have in bodies, in human bodies, you have hemoglobin. In plant leaves, you have chlorophyll. The visible spectrum is full of strong chromophores. As soon as you go into the near infrared, that situation changes radically, and that's physics. It's because, visible light has enough energy to move electrons around in atoms and molecules. So you can build chromophores which are very strong and very sensitive to being changed by an incoming photon. As soon as you move into the near infrared, you don't have enough energy in the photons to move electrons around in atoms and molecules very easily. I mean, there are a few, but those interactions tend to be very weak. You begin to run into water, which absorbs weakly as you go into the infrared. The water absorbs more strongly the further you go into the infrared. You're just seeing the high overtones of the vibrational bands of water in the visible and near infrared. So as soon as you move, let's say beyond 700 nanometers, you've run out of pigments. You don't have any pigments. You don't have any chromophores. Nothing's colored anymore. In fact, if you look at you're wearing a black shirt, aren't you? I bet you if you took an infrared photograph of that black shirt, it would be white.
Yeah, yeah.
Because there aren't any pigments in the infrared. And so as soon as you start looking at light entering the body in the infrared, you're in a totally different scenario. In the visible, you're dominated by absorption. In the infrared, you're dominated by scattering.
Mm-hmm. So most of the light that we can see, that we use for image formation, when it hits our body, it gets absorbed by stuff of the body.
Yeah,
but not so much for the longer wavelength light like near infrared.
Absolutely. And what happens if an infrared photon, say at 800 nanometers, an infrared photon hits my skin,
mm-hmm.
It'll penetrate probably a couple of millimeters at 800, maybe even more at 800 nanometers. It'll propagate untouched to a millimeter or so, and then it'll hit something, which will be a cell wall, say, and it'll scatter. And since there are no pigments around, it won't get absorbed because there's nothing to absorb it. So it'll scatter. And, some of the light will scatter straight out again. Some of the light will scatter deeper. Some of it will scatter sideways, and it'll perform a random walk through the body.
Mm-hmm.
And this is what happens to the infrared photons. They bounce around many times inside your body.
Mm-hmm. They kind of get stuck in your body. They're pinging around.
They're pinging around until they get absorbed by something, and the absorbers are very rare. Mm-hmm. And have you seen the famous picture of my hand?
Yes,
with the veins.
Yes.
Deoxygenated hemoglobin has a significant absorption in the near infrared, and that's why my veins look dark. It's it's projected against the diffuse light.
That's why, if you go, anyone who has a red light at home, you often, if you look at a mirror, you can kind of see all of your vasculature very clearly.
Yeah, exactly. And in fact, if you get a lamp and you put your finger over a flashlight, you'll see red light coming through.
Yeah.
And you think, oh, that's due to hemoglobin. No, it's not. It's due to the sunset. It's scattering. And you scatter the short wavelengths first and the long wavelengths.
So there's a lot of this near infrared light coming out of the sun. Life, in some sense, seems to be tuned to it. And when that light hits our bodies, it pings around inside of our body for quite a while, but eventually it will run into something that can absorb and interact with it.
Yeah. And that's the point. But that's the first order answer to this question. It actually gets more complex and more interesting than that. We can follow this scattering. I mean, I can do it here with my spectrometer. I can shine light into my hand and I can look at light coming through the other side. And I can measure the distance the light's traveled by measuring the water absorption in the light that comes out. Because half our body is water.
Mm-hmm.
And if this light scatters many times, it takes a longer path through my body than just going straight through. And it could be much longer, a factor of 5, 6, 7 times longer. And it will suffer all the way. It will suffer from water absorption. So when I measure the water absorption coming out of the top of my hand, I can say how far it's traveled through water.
Yeah.
It's quite a long distance that it travels through water. So, that's one experiment you can do. It's actually a flawed experiment, but the idea is there anyway. So what happens, and this is very important. This is, do you know about IKEA stores, furniture stores? Do you have them?
Yes, IKEA.
Yeah, you know all about IKEA. When you walk into an IKEA store, they take you all the way around the store in this zigzag path, don't they?
Yes,
For
yes.
miles before you get out. That's what the photons do in your body. They
Hmm.
scatter many times. Like a pinball machine, you scatter into a pinball machine
Yeah.
and you get bounced around by lots of pins, which don't give you any prizes. And eventually you might win a prize.
Hmm.
It's like an airport departure
Hmm.
lounge. They
Hmm.
take you through all the duty-free places
Right, right,
through
right.
this zigzag path
Yeah.
before you get into the lounge.
So this
So
light is
it's a
kind of
really,
going everywhere in the body.
yeah, it's going everywhere. And of course, taking a long time to do that. So if you get, so many photons per unit volume hitting your hand, it's like cars going down a freeway.
Hmm.
I'll try and speak American. It's like cars going down a freeway. They're all driving at, say, 50, 60 miles an hour, whatever they do. And, you get a lane closure and suddenly you get a blockage and they're all going at 1 mile an hour and they're 2 meters apart instead of 100 meters apart. So what happens when these photons go into your body? They scatter many times and the photon density builds up because they keep coming.
Hmm.
They're not being absorbed very quickly. And so it's like pumping up a balloon with a small hole. You pump up the balloon with photons, and you increase the pressure in the balloon, and you get
Yeah,
lots and lots
yeah. You're
of photons in
accumulating
the balloon.
near
So
infrared
you've
light.
you've got a very high photon density in your body, which is looking for somewhere to be absorbed. Some of those photons will escape the other side, and we see that in the paper that you wanted to talk about. We can shine light right through the chest from front to back. So some of the photons will get absorbed, but there'll be a lot of photons in there. So you've got quite a high photon density inside the body, more than the outside. It's a bit like shining light through a high refractive index window.
Hmm.
The light will slow down because of the high refractive index. And so in that distance, you'll get more photons than you would without the glass there. So, it's not anti-physical, it's a simple physical phenomenon.
Hmm.
But by doing multiple scattering inside the body, you're slowing the photons down effectively, and you're increasing the local photon density inside the body. And so inside the body, we have various structures which could harvest and use light for performing these metabolic functions.
Hmm. So
And
what are some of the
I mean, that's the,
physiological and metabolic consequences of this near infrared light that gets into our body?
well, it enables you. The first thing it does is enable you to produce ATP faster because
Hmm.
you get electrons down the electron transport chain faster than you would otherwise.
And
So
how
you
does that
take
work exactly?
you take electrons from the food. You feed them into the mitochondrial complexes. They go down through the complexes and they work their way down the electron transport chain. And you pump the protons across the barrier, and it drives the turbine in the ATP synthase. So the faster the electrons go down this electron transport chain, the faster you'll pump protons, and the faster you'll drive
Hmm.
this turbine.
But how does the light tie into the speed with which that all happens?
Well, this is this is what I'm coming to. There are a number of ways that this could happen, I think. One of them, and this has been discussed for a number of years now, one is that these photons can interact with chromophores within the complexes in the mitochondria within the electron transport chain.
Mm.
And cytochrome C oxidase, that is one which does absorb in the infrared and is thought to be responsible for some of these processes. So there are chromophores there that can absorb photons. And for a long time, we thought this was the case. So we were searching for the wavelengths associated with these chromophores, but we couldn't really find any preferred wavelength. All the wavelengths all the wavelengths in the infrared, near the red and near infrared, seem to work very well. And I think now that's not the way the interactions are happening. I think it's most likely that the energy interaction between the photon and the biology, the movement of the electron, is likely to be mediated by the water molecules because water has weak absorptions in that spectral range. It can easily absorb um, infrared photons. And there's a lot of work on, the effect of infrared photons on the structure of water. Pollock and people have worked on the fact that photons influence the structure of water, enabling it to be less viscous and so on. And this may also play a role. But I think what's happening is that the water molecules are getting absorbing these photons, changing their vibrational state with an amount of energy which is sufficient to drive this half three-quarters of electron volt metabolic process. So it's able to enable the electrons to get down the electron transport chain faster
Hmm.
by enabling, rather than quantum tunneling and doing it slowly,
Hmm.
you can do it quickly by hopping over
Yeah.
these barriers down the
So,
and
so how do different wavelengths of light, like near infrared, affect the membrane potential of mitochondria? Have we actually measured that? Do we know that for sure?
well, yes, we have measured the membrane potential. Yes, that has been measured, I think, by Glenn's group before. I'm not very familiar with those experiments, but we can certainly measure the rate of production of ATP.
Hmm.
And I think yes, it is possible to measure the membrane potential, I
But
believe. But
near infrared light can increase the rate of production of ATP in a mitochondria.
yes, yes. I mean, I'm not going to talk much about the medical effects, but there are other people who can do this very well. Glenn Jeffrey himself, will do
Hmm.
this, and Roger Schwelt has done a number of, in fact, very recent podcasts. I don't know if you've seen his
Yes,
podcasts.
yes, yes.
He talks about the medical effects. You can certainly improve mitochondrial function with
Yeah,
infrared light,
yeah.
and
So
we
this
think
this
that
isn't just theoretical. Like,
no, there are many experiments now, and so I mean the question on the table is exactly how the infrared photons do that.
mhm,
What the quantum mechanical interaction
yeah.
is.
And you think it could be
And
via interactions with
I
water?
I don't have the answer. We're thinking about this. I'm not in my study here. I'm not equipped to do those experiments, but there are people who are.
Hmm.
So we're saying that, we think. And interestingly, one of the people who's always on the Guy Foundation seminar series is Wayne Frash from Arizona, and he's the person who studied in intricate detail the transport of photons through the ATP synthase. And he has realized that the protons uh, are shepherded through this turbine with water molecules.
Hmm.
And there was a very interesting seminar in this series just a few months ago by Nathan Babcock at Howard University. He's a young quantum biologist who works on properties of water. And he was talking about the way you can move electrons from one molecule to another molecule to transport charge by noticing that the charged molecule will be surrounded by oriented water molecules because water is so polar that the charge on the molecule will orient the water molecules, and that orientation will change when the charge is moved from one molecule to another one. So
Hmm.
you'll have to basically move those oriented water molecules. You have to move their structure to another molecule, which will require energy because the orientation energy is related to the charge of the electron, and the energy that you need to orient these molecules is of this order of magnitude. It's a fraction of an electron volt. So what I suspect may be happening here is that you're using the water as an intermediary by using this photon energy to excite the water molecule and give it the energy necessary to move the electron from one
Hmm.
place to
Hmm.
another.
Hmm.
So it's a
How do,
facilitator of electron motions. And
yeah. I want to talk a little bit about how, so when we think about human life on the planet and the way it's progressed, our
mm,
light environment has changed radically over time, and it's
yeah,
changed especially radically in the very, very, very recent
yeah.
past. We now are spending more time indoors. We're spending less time, out walking through the woods and
Mm.
nature and things like this. How is the modern light environment today different than it used to be when we lived a different way, especially in
Yes.
terms of the near infrared light spectrum and the full sunlight spectrum that our bodies are exposed to?
Okay, well, actually, I was going to start with this because I was going to say this is the problem we're addressing at the moment. And I think the first point I'd make about this whole point is this whole argument is that we're trying to re-establish a status quo that was present 50 years ago in life. What we've done has been to change the light environment radically over the last roughly 50 years. I mean,
Mhm.
since the invention of the fluorescent tube and subsequently the invention of the white LED, we have radically changed the light environment. Before then, basically all the light sources available to us were what we call thermal sources. That is, they emitted thermal radiation, Planck spectrum.
Mhm.
The sun, fires, oil lamps, candles, gas lamps, they were all thermal sources. So they were all emitting strongly in the near infrared as well as in the visible. In fact, the problem with all these light sources was to make enough visible light without making too much infrared light, because a lot of the energy was going into making infrared light. And so there was a historical drive to get away from, say, the Edison light bulb, which, is was, ubiquitous for making light inside buildings, but of course used most of its energy making infrared light, which was not visible light.
Hmm.
And so we wanted to get rid of the tungsten filament
We were
bulbs.
thinking about it
And
as waste because we didn't realize we were
it was a
using it.
waste, yes. We thought of it as being a waste. That turned out to be a big mistake. But
Yeah.
but anyway, so we got to the white LED. We're driven by a blue LED, which won the Nobel Prize in, what was it, 2012, I think it was, um, for making the perfect light source. And so we honed these lights to produce visible light only and produce no shorter wavelength and no longer wavelength, just inside the visible spectrum. And this seemed to be okay. We could see perfectly well. A lot of people didn't like these shiny white LEDs. They found them very uncomfortable, but they certainly produced visible light. Um, but that coincided with a very slow process in what I would call the decay in public health.
Hmm.
Public health has, in some senses improved, in some senses it's decayed, but it has decayed significantly over the last few decades. And I think the rate of increase in lifespan has slowed pretty much to zero now. And a lot of people are getting sick. And we've got a huge explosion in type 2 diabetes and obesity and other diseases of aging. So this was the clue that we saw to the relevance of non-visible light to human health, or to the health of the whole biosphere, in fact. So what we've actually done has been far more dramatic than just changing the light bulbs. We've actually, because we're building glass coated buildings now, we've changed the windows so that the windows also only allow visible light into the buildings. So we end up with white LEDs in rooms and buildings with windows that are only letting from the outdoor environment, are only letting
Mhm.
visible light
Yeah.
inside
Obviously,
the
we
building.
obviously we see with visible light, but our
So we
bodies
don't
use
notice.
other
We don't
forms of
notice.
light,
Yeah.
and we overlooked that.
We overlooked that, yes. And, it turns out, I believe, to be one of our biggest mistakes. And now we have people spending the majority of their time, many people spend the majority of their time within the built environment, and they're getting sick. And we had the famous case of the astronauts on the space station
Hmm.
who came back with very poor health.
Yeah.
And the analysis of the paper in Cell in 2022, whenever it was, showed that the common feature of the astronauts and all the experimental animals they sent up to the space station, they all came back with mitochondrial dysfunction.
Mitochondrial dysfunction. So they were in a impoverished light environment, and the environment differed
That's
in other
well,
ways as well.
that was our proposal. In fact, the Gaia Foundation wrote a long report about space health and sent it all to all the space agencies a few months ago now, where one of the factors in there, there are many factors in there, microgravity and ionizing radiation and all those
Mm-hmm.
things, but one was to do with non-ionizing radiation, i.e. the light environment. And of course, these guys are sitting in a tin can lit by white LEDs.
Yeah, yeah.
I mean, they changed the lighting in 2012. They changed it from a mixture between fluorescent tubes and I think tungsten filaments in 2012 to all LEDs. I mean, they introduced the circadian variation in color and brightness, but they're still all LEDs, and so they're completely infrared dark. So there's no infrared in the space station at all.
Wow.
And so they were living in a completely infrared starved environment for many months. And I think this happens in other infrared starved environments as well. And I'm
Hmm.
sure if you looked at submariners, you'd find they came back sick. We don't know about this because we're not told, but I think these light starved environments and the symptoms actually are very like scurvy. I mean, scurvy was the absence of vitamin C. What I call this 21st century scurvy, it has symptoms which are very similar to vitamin C. The symptoms develop over timescales of months and years, not immediately. But all the diseases of aging are determined essentially by the mitochondrial function. And when you
Yeah.
destroy or slow the mitochondrial function, you increase the rate of aging and you reduce the metabolic efficiency of the life form.
Hmm.
So, our view is that this is, there are many causes of obesity and type 2 diabetes, and junk food being not the least of them. But I think a primary cause of this is the light environment.
Hmm. Yeah. So basically, what you're saying is a major contributor to mitochondrial dysfunction, which is going to underlie all kinds of things from metabolic
Mm,
diseases to aging itself,
yeah.
is an artificial light environment with a lot of emphasis on a lack of sufficient near infrared light, which the whole planet is naturally enriched in, that we
Yes.
are now depriving ourselves of. And that's because this is giving us a less efficient energy metabolism.
Exactly. Yeah. Yeah. Except I wouldn't say we're doing it just to exclude non-visible light. We're choosing this lighting for high efficiency,
Right, right.
high energy efficiency to make visible light. And the point we've missed is that you need more than visible
Yes,
light
yes.
to thrive.
Yeah.
So
If you,
you're saving energy, but you're
right.
developing huge health costs
Right, right,
in
right. Because people think, people are thinking of light only as visible light to see with, and therefore, if you have, an incandescent light bulb or something, it's going to drive up your costs because you're producing all of this quote unquote wasted light that
yeah,
you can't see. But
yeah,
in fact, it's not wasted light because it's being used for things besides vision.
exactly. And I use them all the time. This is a 60-watt tungsten filament lamp
Yeah.
run at slightly lower voltage. It doesn't you didn't don't need it to run at full voltage because you don't need to generate lots of visible light. I have
Mhm.
LEDs on the other side to give me visible light.
Mm,
But this gives me healthy light,
I
and it
see.
gives me quite a lot of visible light as well. But it's so easy to do, but this is of enormous value.
I
It
see.
has
So you can just
enormous,
you can run a light like that will give you that near infrared light, and you can do it at a lower voltage
yes.
to save on your energy costs, but then still get that near infrared light.
I can hold this.
Yeah,
I'm
yeah.
holding this in my
Oh
hand. You
wow.
couldn't do that with a full voltage infrared lamp,
Yeah.
tungsten filament lamp. So the point is, to get over the regulation. I mean, it's going to be illegal and it is illegal in the US to use tungsten filament light bulbs now, isn't it? It'll become doubly illegal next year when you have this new regulation, which requires a certain number of lumens per watt.
Hmm.
Um,
So you are using that light in your home.
yeah.
If you can't do that, would you just emphasize getting outdoors as much as possible?
Well, first of all, I would emphasize getting outdoors. I think getting
Yeah.
outdoors is absolutely crucial. And what we're saying, and all the experiments we're doing with infrared light, is based on brightnesses that are not significantly more than the brightness you'd get at the sun from
Yeah.
the sun at that wavelength. So the experiments we're doing, I think, are safe because we're not doing anything more than the sun would do.
Mm-hmm.
So we're not using lasers. I wouldn't ever use lasers for this kind of purpose because they can do all kinds of damage to do with their coherence rather than their
Yeah.
wavelength.
Yeah. And so much of what we've talked about ties into mitochondrial health and metabolism.
Mm.
One of the things that struck me in the new paper that you wrote that I didn't know about before
Mm.
is that apparently the outer retina contains more mitochondria than any tissue in our body.
Yeah, yeah, yeah.
What can you start to tell us about the modern light environment and the health of our eyes, given how we've messed up our light environment and now we're exposing our eyes to a very different pattern of wavelengths than we've adapted to as a species?
Well, first of all, I mean, I learned all this stuff from Glenn Jeffrey when I first worked with him, and I mean, he coached me, and he said, in the cones in your eye, it takes huge amounts of energy to once you've detected a photon, in order to reload that cone cell, you need a very high input of energy. It's like loading a crossbow, okay? And when you detect the photon, you're hiring the crossbow and sending the crossbow into the nerve system to send a signal to the brain. But
Mm-hmm.
the cells in the retinal cells in your eye are far richer in mitochondria than any other cells in your body, and also they use energy all the time for reloading themselves, even in dim lighting. So they're very demanding of well operating mitochondria, and so the eye is a sensitive metric of failing mitochondrial function. And this was driving the work on early stage macular degeneration, where you could slow the macular degeneration as long as it hadn't progressed too far. You could
Mm-hmm.
slow it by shining this infrared light, or red or infrared light, into the eyes. This infrared light will get into your eyes without going through the pupil, of course. It'll shine in sideways. It's the
Mm-hmm.
reason we can't see in the infrared. We couldn't build an eye. We
Yeah,
couldn't
yeah,
build
I get
an
it.
eye
Huh.
which was opaque enough to make
Yeah,
a camera because it gets in through the eyeball, no trouble at
yeah,
all.
yeah.
So the retina is irradiated by this, certainly by the longer wavelength, the longer near infrared wavelengths, around a micron or so. The light gets through the whole eyeball. So, it's rich in infrared light, which increases mitochondrial function. It doesn't have to go through the pupil at all. So, yeah, I think the message is to make use of natural infrared light, because the kind of infrared light we're getting there, we've adapted to, and there are factors in that which are different from the artificial lighting that we use. I mean,
Yeah.
the light coming from the sun has the water absorptions in it from the atmosphere. So there are some of the infrared wavelengths in the sun are much brighter than others. There are
Yeah.
these windows in the sun. We're very familiar with them in astronomy because we use these windows to observe from the ground in the infrared. And we can't observe in the water bands in the infrared. So we have distinct bands in
Mm.
astronomy that we can use to look at
Hmm.
the sky in the
Yeah.
infrared.
So to put it simply, the light from the sun, near infrared light, is never going to be identical to something that you can generate in your home from a bulb or from a red
No,
light device or whatever.
we can generate infrared light, which is right up there with the brightness of the sun in a lamp like this. Now, this lamp is roughly as bright as sunlight at 1.5 microns.
Hmm.
I mean, it's very much weaker what I can see with my eye, many times weaker. But if I look at this in the infrared, it's quite a lot brighter.
Hmm. And do you just have that on all the time when you're in your study?
Pretty much all the time when I don't get sunlight shining through the window. My
Hmm.
window is not infrared absorbing, so I can get
Oh,
some
okay.
light from the outside. But yes, I have it
Yeah,
on, and I don't have these everywhere. I don't have them in hallways and
yeah,
in
yeah.
bathrooms and so on because you're not there very long.
Hmm.
We use LEDs for
Yeah.
those, but in the kitchen I have LEDs and tungsten filaments.
Hmm.
In the bedrooms we have them as bedside lamps. We have tungsten filaments, and also use them for reading
Hmm.
in the sitting room.
Yeah. But I mean, based on what you've told me about what's coming from the sun, what's being, reflected and absorbed in the atmosphere,
Hmm.
the reflection that comes from vegetation, it wasn't as if, back in the day, humans were only getting near infrared exposure the first hour and the last hour of the
Hmm.
day when the sun was low. They would have been getting a lot more
Well,
throughout the day.
yeah, yeah, fine. And this was realized, of course. I mean, Florence Nightingale realized quite clearly that people healed much more quickly in daylight. And she said the first thing is fresh air, the second thing is sunlight. That was 100 years ago.
Hmm.
And we've forgotten this.
We've
You know,
forgotten it.
hospitals used to be built with terraces where you could wheel people out into sunlight.
Yeah, yeah,
Listen to Roger Schwelt talking
yeah,
about the people he's put out in sunlight, in COVID
yeah.
and with other diseases. I mean, it's so obvious that it works superbly well. You look at photographs of masses of people in the 20s and the 30s. You don't see obesity. Type 2 diabetes was not a common disease then. It's changed dramatically. The types of diseases we're suffering have changed
Hmm.
dramatically in the last
Hmm.
decades. And I think this is due to the light environment.
Yeah. You think a substantial fraction of the metabolic disease that we've seen unfold over the last century, including obesity and diabetes, could be in large part because energy metabolism in our mitochondria is less efficient because we're no longer in the optimal light environment.
Yes, it's not the only contributor. I'm
Sure,
not saying it's
sure.
the only contributor, but I
But it's
think
a
it's a
major
very
contributor
significant.
and an overlooked one.
Yeah. And well, it's less overlooked now. I mean, people are
It's
listening
starting to
now.
change. Yeah, just, I mean,
Yeah, it's
you can
starting to
really
change.
tell
I
the
mean,
last couple of years.
architects are listening to us. Lighting designers are listening to us because they love it. They hate LEDs because they create awful light environments. People
Right,
don't like them.
right.
And so, if you're a high-end light designer, you'll be very happy to be able to use uh, infrared-friendly light bulbs.
Yeah, yeah.
So, and the architects, of course, are worried that they're going to be accused of building toxic buildings, which they are. Take the occurrence of type 2 diabetes in Saudi Arabia for the people who live in the skyscrapers there is currently around 36%. I think it's huge.
Wow.
So this is a very, very big deal. And
Wow. Well, Bob, I don't want to take too much more of your time because we're close to our time here. Um, are there any final thoughts you want to leave people with, or anything you want to reiterate about sunlight and the question of what is life?
yeah, I want to emphasize first of all that what we're trying to do, we're not generating circadian lighting. We're not doing photobiomodulation. We are, but not, that's not the aim of the exercise. What we're trying to do is to educate people to the conclusion that we need natural lighting. It's not something you can ignore. If you put yourself in environments where you're never given an infrared rich source of lighting like daylight or firelight. Firelight, wood fires are pretty good for producing infrared. I think this is the only reason people survive at high latitudes in the winter when it's completely dark, and they use fires a lot. And I think the message we want to put over is, don't be afraid of the sun. The dermatologists are coming to realize this as well. it's silly to go and sit on a sunbed for 2 weeks a year with nothing on and burning yourself to a crisp. Use daylight, but use it intelligently. If you're going into lots of ultraviolet light, wear clothes to cover up. Uh, if you want to sit in healthy places in daylight, sit under the shade of a tree.
Hmm.
Shade of a tree is absolutely superb because it protects you from the direct sunlight, which contains the ultraviolet. You're probably wearing clothes anyway, but it protects you from the direct ultraviolet radiation. But you're being irradiated by near infrared from the tree, and it's dramatic. If you walk outside with an infrared spectrometer, you walk into a wooded environment, you're absolutely flooded with infrared radiation. So, and the Japanese go tree bathing, they go forest bathing, and it's very sensible. They may not understand how it works, but it's
Hmm.
extremely sensible.
And so you've got sunbathing, you've got forest bathing, and based on everything you've told us, forest bathing is a form of sunbathing.
Absolutely, and it gives you the best part.
Right, right.
Newton thought of gravity. I'm sitting under an apple tree, and that's not an accident. I say, in fact,
His mitochondria were fully functioning.
it was fully exactly. So that's the first point. I think the other point I would make is, as if we're talking about remedies, how do we change the current situation? I don't think it's costly. I think the health costs that we're accruing by infrared starving people are huge. The cost of diabetes, the cost of obesity is huge. The cost of changing the light environment, I think, is small. It's certainly small in terms of changing the light sources. I think the question of the windows and the transmission of the windows is more difficult because if you're going to build these big buildings with covered in glass, you're going to have proper thermal management of the buildings, and that's difficult. I think in the future, you may be able to design glass which satisfies all the criteria that you need. It lets in the amount of infrared that you need for healthy living. It uses non-visible wavelengths to produce electricity as solar panels, and it can control the thermal properties, the input and output of the thermal properties of the building as well. So I think you need clever glass, which perhaps we haven't invented yet, but will be very interesting to think of. But the thing about buildings, I think if you go into a building, you find the whole building is lit. And if you go outside, you find people are using enormous amounts of light for security reasons. I think that's an absolute nonsense. You're much less secure in super bright security lighting than you are in very dim lighting. So you move the lighting to where people are. So you associate lighting with people rather than spaces. I think this is one fundamental principle. You don't light spaces, you light people. And if you light people and you use the heating budget, part of the heating budget, to light people with infrared radiation, and you shine it on the people, and the people will use that infrared radiation to generate useful metabolic function that'll make your mitochondria work well. You'll still excrete that heat into the building. So all you're doing is you're passing that heat through the body before you pass it into the building. And that means you're not wasting that heat at all. You don't need to use the whole heating budget of the building, I'm sure, but use part of it to illuminate the people with sensible lighting like this.
Hmm.
And you're not wasting anything.
Wow.
And you're making people healthier.
Yeah. So all of this has, this understanding of light not only has implications for biology and health, but for space and architecture and design of
Yes,
where we
absolutely.
spend our time.
Yes. I mean, I've been talking to the chairman of the Guy Foundation, the originator of Guy Foundation. He's building an orangery on his house and he wants to light it intelligently. And we've decided, where you put the infrared absorbing glass, where you put the infrared transmitting glass, where you plant the plants outside the building. If you plant trees on, on north-facing windows where the sun can see the tree, but you can't see the sun, you can radiate lots of infrared light into the building from the tree. So having vegetation around a building, especially if the vegetation is directly illuminated by sunlight, is enormously valuable. So there are all kinds of principles here which can be used for intelligent, non-wasteful lighting. But I think for the inside, the principle I would adopt is have in your head, illuminate people where they need it. And if people don't need lighting, don't use it. Only switch it on when you need it. And follow the people around with the lighting.
Light is for illuminating people, not spaces.
Yeah, right.
All right. Well,
we could reduce the amount of lighting we use enormously. Huge factor. We'd save huge amounts of money. Much more than it would cost us to make these decisions.
All right. Well, Robert Fosbury, thank you very much for your time. This is fascinating, not only like the biology that I often talk about on this podcast, but really understanding all of this stuff from a more physics perspective and a cosmological perspective.
Yes.
Some of what you told me about stars and the analogy between stars in the universe and life forms is really, really going to make me think.
Well, it's been a great pleasure to talk to you. In fact, this is a bit different from talks I've given previously on podcasts because I've thought a bit more about the cosmology, and we are thinking a bit more detail about the details of the energy transfer between the photons and the biology. And I think that's something that really needs to be, and it's likely to be quite complex. I think there are likely to be many, many pathways where the energy is traversing this distance between the sun and the biology. Because biological evolution doesn't work in simple ways. It makes complexity. It uses all available physical processes without worrying about whether it knows how it's working or not. It just uses them. So I think we'll have a hard job to really understand what's going on with what I call photometabolism. But if you think about it, it took 250 years to work out how photosynthesis worked. From the first discovery that photosynthesis was happening to pretty much understanding how it's worked. Well, I'm sure it's not fully understood yet. Some of the quantum effects in photosynthesis are pretty profound as well. So there's a long way to go. But I think yes, we have to make changes. We would prefer people to make changes by using natural sources. But if you can't use natural sources, you have to think more about the way we light and heat buildings. But the architects and the lighting designers are perfectly capable of doing that. So, yes, okay. The one thing I did want to mention as well about being outside, not only do we get the infrared benefits from the vegetation. Imagine if you're sitting outside under a tree on a clear day, you've got a blue sky all around you. You shaded yourself from the sun by sitting under the tree. Your body is exposed to a huge solid angle of blue sky all around you. Now, think about that blue sky. If you ever pointed one of these radiative thermometers at the blue sky on a clear day, you'll find it will read about -40, -50 centigrade. But the sky is very, very cold. A clear sky is very, very cold. Outer space is -270 degrees centigrade, but the blue sky is also very cold, depending on the amount of water vapor it has. If I'm sitting in this room, the wall around me is 25 degrees centigrade. My body is at 37 degrees centigrade. So I'm operating a heat engine with a temperature gradient between 27 and 25 between 37 and 25 degrees, which is not very much.
Yeah.
So I can only produce about 5% of the energy that I eat. I can only use about 5% of that for useful energy. If I was sitting under a blue sky outside, I would be able to use more than twice that amount of my food for useful energy. Because I would be able to radiate my excess heat and entropy to a very cold surface. So in this sense, the body is like a heat engine. I have a heat engine on my desk here. You can just see it going. That's working on a temperature difference of 4 degrees centigrade. If I put an ice pack on that, I can run it 10 times as fast because of the temperature difference. We do exactly the same thing. When it's close to body temperature, you have no energy. You feel it.
Right.
If you go and go out and sit on a bench under a clear blue sky, and you'll feel great. You'll feel much more full of energy. And this is just the second law of thermodynamics.
Yeah, you can get rid of that heat faster.
Yeah. So, in fact, if you wanted to have office workers who were working much more effectively, you'd make them sit in a cold office. And they wouldn't like it, but you could give them warm clothes and they'd still be breathing in colder air, which in the air has lots of surface area.
Right.
So this is why, a lot of the inventions of the Industrial Revolution happened at high latitudes because people were in colder environments. The navvies who built the canals and the railways, they were eating 8,000 calories a day and they were doing huge amounts of work. They couldn't have done that in the tropics. It was thermodynamically impossible for them to have done that in the tropics. So that's the point I want to make. There is a thermodynamic aspect to this, and there are heat engines in our bodies associated with both temperature, kinetic temperature, the temperature you measure with a thermometer, and with radiative temperature. The sun is at 6,000 roughly. Outer space is at minus 270. And we are working between the sun and outer space. So we're subject to this much bigger temperature gradient between the radiation coming from the sun and the radiation going out into outer space. So that's another fundamental physical principle associated with this.
Visit mindandmatter.substack.com to find all of my content. If you like to read like I do, then you should check out the ReadWise app. It's totally free to download, and if you go through the link in the episode description or on my support page, you can get a free 60-day trial for zero cost. ReadWise is a really cool app that allows you to import digital highlights from over 30 different platforms such as Kindle, iBooks, PDFs, and more. It makes it really easy for you to review and find and share excerpts and quotes from whatever it is that you're reading, whether it's PDFs of scientific papers or books that you're reading on your Kindle. And you can even save and use highlights from physical books. I read a lot of physical books before bed, for example, or when I'm traveling. And the ReadWise app actually integrates with the camera on your phone so that you can take a photo of a page that you're reading, highlight a specific chunk of text from that page, and export it to the app so that you can reference it or find it or share it later. They even allow you to export really cool looking graphics of some of the highlights that you have in the books or the papers you're reading so that you can share them in an engaging way. So check out the ReadWise app today if you are a reader and you like to reference and organize what you read. Go through the link in the episode description or on my support page or in my free weekly newsletter at mindandmatter.substack.com and try the ReadWise app 60 days free today.